We will now look at an example to calculate the mean value or ensemble average, deviation, dispersion or variance, as well as standard deviation. Consider a system of four non-interacting spins in the absence of an external magnetic field. So this is referring to having spins that have random orientation, and the distance between these spins is large enough that they are basically blind to the magnetic field that comes from the neighboring spins. There is no interaction between them. Okay, so this is an n equals to 4 ideal spin system, and the external magnetic field is 0. And remember what that means. The probability P of having up orientation is equal to the probability Q of having down orientation equals to 1/2, because there is no preference for up direction over down direction. Find the average number of upspins, variance of the number of upspins, standard deviation, average total moment number, variance, and standard deviation of the total moment number. In order to answer these questions, as you know, we need to know all the possible scenarios and their corresponding probabilities. So probability of having n spins pointing up out of 4 spins is given by combinations of 4 spins taken n at a time, p to the n, q to the capital N minus n. That's the binomial distribution. So what are the possible values of n I can have? So let's list them here. N can be 0, 1, 2, 3, 4. All of them are up, or there's no down. The corresponding total moment number, basically remember what this total number was. The total moment I show with capital M. This is total moment number times n total moment number times mu 0, where the total moment number is n minus n prime. So corresponding to this n equals 0, 1, 2, 3, 4, I have n prime equals 4, 3, 2, 1, 0. That means the number of down spins is, and plus the number of up spins has to be equal to 4. So n plus n prime has to be equal to capital N. That's 4. And what is the corresponding total moment number? M, n minus n prime can be minus 4, can be minus 2, 0, 2, and 4. So these are all the possibilities. Now I would like to list the corresponding probabilities. Probability of having an n value here is, this is something we have done before. We have calculated these probabilities. It's going to be 1 over 16, 4 over 16, 6 over 16, 4 over 16, and 1 over 16. Now that I have listed all the possibilities, possible scenarios, and the probabilities corresponding to these outcomes, I'm ready to answer the questions. So let's start with part A. Find the average number of up spins, n bar. So n bar, by definition, is the probability of having an n value multiplied by n value, where n goes through all of its possible values from 0 to 4. So this is going to be equal to So let's look at these one by one. N equals 0 corresponds to a probability of 1 over 16 plus n equals 1 corresponds to a probability of 4 over 16. Then I have n equals 2, 6 over 16, n equals 3, 4 over 16, and n equals 4, 1 over 16. So if I add these numbers, I will get 0 plus 4 over 16 plus 12 over 16 plus 12 over 16 plus 4 over 16. So this will be over 16. So I will end up getting here for n bar, therefore n bar is equal to 12 plus 12, 24, 28, 32 divided by 16. Therefore my answer to this question is n bar must be equal to 2. The average value of the number of upspins, or the ensemble average, must be equal to 2. Let's look at part B of the problem. Part B asks me the variance of the number of upspins. Okay, so the variance delta n square bar is basically n minus n bar square bar. So in order to find this, I need to know what is delta n square, or what are all the possible values of delta n square. So let me note here again the possible values of n was n equals 0, 1, 2, 3, 4. The corresponding possible values of n minus n bar, delta n, that's the deviation, the corresponding values are n bar is equal to 2 here, which is what I found in part A of the problem. So it's going to be 0 minus 2 minus 2, 1 minus 2 minus 1, 0, 3 minus 2 is 1, 4 minus 2 is 2. So what are the corresponding delta n square values? It's going to be 4, 1, 0, 1, 4. Now I'm ready to take the average of delta n square. Delta n square average is by definition going through all possible values, delta n square multiplied by probability of having an n value. So this is going to be equal to, if I multiply it with the corresponding probability, so let me remind myself here, 1 over 16, 4 over 16, 6 over 16, 4 over 16, 1 over 16. So I will have 4 times 1 over 16 plus 1 times 4 over 16, 0 times 6 over 16, 1 times 4 over 16 plus 4 times 1 over 16. So if I add these numbers, I will get 4 plus 4 plus 0 plus 4 plus 4 divided by 16. So it's going to be 16 divided by 16. Therefore, the variance is delta n square bar is equal to 1. So this is the answer to part B of the problem. Okay, so let's look at part C. Find the standard deviation in the number of upspins. This is quite simple once you know the variance. Standard deviation, we show it with delta tilde n, is square root of the variance, 1/2, or we also call it root mean square. So it's going to be equal to square root of 1. Therefore, the standard deviation is 1. So basically, let me remind myself what this means. Most of the values of n will be in the range n bar plus or minus a standard deviation of n. So n is 2 plus or minus 1. So this is where most values of n will lie in this binomial distribution. So let's move on to part D of the problem. In part D, we would like to know the average total moment number m bar. So I can answer the questions about m in two different ways. First of all, I will use the definition. So m bar is something I can calculate by definition, looking at all possible values of m. M goes from -4, so let me remind myself possible values, to +4 in units of 2, but I shouldn't show this with the summation sign because it's not increasing one by one. So let me say that this is going to be, for convenience, let's write down these possible m values here again. -4, -2, 0, 2, 4, corresponding probabilities of m values. And at this point, I remind myself that m is n minus n prime, or n minus n minus n, so that is 2n minus capital N, and therefore probability of having an m value is equal to probability of having an n value, so they are the same thing. So I'm going to consider the probabilities for m values: 1/16, 4/16, 6/16, 4/16, and 1/16. So the average value of m will be -4 times 1/16 plus -2 times 4/16 plus 0 times 6/16, 2 times 4/16 plus 4 times 1/16. Okay, so I can calculate this now. -4/16 minus 8/16, 0/16, 8/16, 4/16. As you can see, the answer is 0. The average value of m bar, average value of m, the total moment number, must be 0. There is another way of finding this average number here, so let me note this as an alternative here. Alternatively, you can look at this equation, m equals 2n minus n. So if you take the average value, average of this equation, that basically means you have m bar is equal to 2n bar. The average of capital N is capital N. So this means it's going to be 2 times 2 minus 4, which is 0. So I can get the same answer using this relationship as well. Let's look at part E. In part E, I want to know the variance of the total moment number, delta m square bar. Again, I'm going to do it the long way. So let's write here once again, these are the possible m values: -4, -2, 0, 2, 4. Average value of m is 0. The corresponding deviation of m is m minus, remember deviation is m minus m bar, -4, -2, 0, 2, and 4. And the corresponding squares of the deviation values, delta m square, will be 16, 4, 0, 4, 16. The corresponding probabilities: 1/16, 4/16, 6/16, 4/16, and 1/16. Therefore, I will find the variance given this information. Delta m square bar must be equal to 1/16 times 16 plus 4/16 times 4 plus 6/16 times 0, 4/16 times 4 plus 1/16 times 16. So I will find the variance in the total moment number to be 16/16 plus 16/16 plus 0 plus 16 plus 16 over 16. So this is going to be 4 times 16/16, which is 4. So the variance in the total moment number must be equal to 4. Okay, now I'm going to look at the alternative method here. So let's look at alternatively. Is there an easier way to see it? Now I have this equation, m is equal to 2n minus n. If you take the delta, the variation of this equation, it's going to be delta m is equal to 2 times delta n. So and I also take the average, so it's delta m bar is 2 times, no, because I'm going to use the square. Delta m is 2 times delta n. Okay. And therefore, what is delta m square? Delta m square is 4 times delta n square. And then what is delta m square bar? It is 4 times delta n square bar. What was the variance of delta n? Of n, it was 1. So this is 4 times that. Therefore, the variance in the total moment number should be equal to 4 as expected from part E. And finally, in part F, I would like to know the standard deviation in the total number. Well, that's very easy, so let me just do that here. So let's, because it's just one line, F delta m tilde is basically the square root of the variance, average value of delta m squared, and that's going to be equal to 2. So most m values will lie in a range. M will be in this range 0 plus or minus 2. M bar plus or minus delta m tilde. Let me put this tilde in the right place here. Okay, so let's summarize what we did here. We went through the exercise of calculating the ensemble average, variance or dispersion, and standard deviation of the number of up spins and the total moment number in an ideal spin system consisting of 4 non-interacting spins in the absence of an external magnetic field. So the absence of the external magnetic field implies there is no preference for up or down, so probabilities should be equal. They are equal to 1/2. And the number of up spins, finding any n of capital N spins pointing up scenario is given by the binomial distribution, combinations of 4 spins taken n at a time, p to the n, q to the capital N minus n. And this is something we calculated before. So the possible values for the number of up spins is 0, no spins up, 1, 2, 3, 4, all spins up. The corresponding number of down spins can be 4, 3, 2, 1, 0. The total moment number is the difference between number of up and down spins, so it is -4, -2, 0, 2, 4, with corresponding probabilities 1/16, 4/16, 6/16, 4/16, and 1/16. Then we added up the product of the possible values of n with their corresponding probabilities, going through all possible values of n. We found the average value to be 2. Then we calculated all possible values of delta n squared, square of the deviation. They were 4, 1, 0, 1, 4, and then we take the average by multiplying them with the corresponding probability of having an n value going through all possible n values, and we found the variance to be 1, and standard deviation or root mean square of the dispersion is 1. And that means the possible values of n will lie in a range between 1 and 3. Most of them will be in this range, 2 plus or minus 1. And once again, that's not the complete statistical description. Complete description is given by these numbers here. And then we looked at m values, all possible m values and corresponding probabilities. Because of the relationship m is equal to 2n minus capital N, probability distribution for m is the same as probability distribution for n. So we have same probability values for these outcomes. And we calculated average value of m by multiplying the possible values of m with the corresponding probabilities to get 0. And then alternatively, I said because m is equal to 2n minus capital N, if you take the average of both sides, average of a constant is itself, n bar is 2n bar minus n, so it is also 0. Then I calculated all possible deviations of m minus m bar. I take their squares, I multiply them with the corresponding probabilities and add them up to get the variance, which is 4. And alternatively, I see that from m equals 2n minus capital N, the deviation in m is twice the deviation in n, and delta m square is 4 times delta n square by taking the square of both sides of this equation and taking the average. Delta m square bar should be 4 times the variance of n, which is indeed 4, because delta n square bar was 1. So it's 4 times 1 is 4. And the standard deviation is root mean square of 4 is 2.